Up until now, you have seen equivalent circuit models of battery cells that use differential equations in continuous time, and we desire to convert these equations into an equivalent discrete time form that would be represented as an ordinary difference equation instead, or ODE, for easier use by the final application, which for us, of course, is in our battery management system algorithms. So, in this lesson, you will learn how to convert a generic first-order linear ordinary differential equation of the form x dot equals a times x plus b times u into an equivalent discrete time form that looks like future x equals a constant times present x plus a constant times present value of u. This conversion process can then be applied to specific cases that we have seen already, and one additional case that you will learn about later on in this week. So the content of this particular lesson is quite mathematical, but we'll take the derivation slowly, step by step, so that you can follow every step and arrive at the final result. And additionally, even though the steps of this derivation in this lesson are a little bit tricky at times, the final form that we come up with will be very easy to apply and practice. So we will come up with a recipe for automatically converting a generic ordinary differential equation into an equivalent ordinary difference equation that's very simple. We begin this mathematical derivation by stating the continuous time solution to the differential equation that we would like to work with. The solution is that x of t at the present time is equal to the exponential of a times t, all multiplying the initial value of x, plus the integral of this exponential of a times t minus tau, multiplying b, multiplying the input signal u of tau as the dummy variable of integration moves between time 0 and time t. This integral is known as a convolution integral in the field of signal processing, and so you may have encountered it before. But how did we get this result? There's a number of different ways of deriving it. The one I show you here is quite short, but it's certainly not an obvious derivation, so let's take it step by step. Step 1 takes the original equation and rewrites it. So notice that we've taken x of t and we leave it on the left side of the equation, but we also take a times x and we move it over to the left-hand side of the equation as well. But that's all that's changed so far. The next step is to multiply both sides of the equation produced by step 1 by e to the negative at. And so you can see that I've taken x dot minus ax and I've multiplied it by e to the negative at. And I've taken b times u of t and I've multiplied it by e to the negative at as well. But this equation that I've listed in step 2 has 3 parts, the 2 parts that we've just talked about, but also this middle one. Where did that middle one come from? Well, if you take that middle one, that says the derivative with respect to time of e to the negative at multiplying x of t, and you compute what that is by the product rule, you say, oh, it's the derivative of the first thing times the second thing, so it's minus a times e to the minus at, all multiplying x of t, plus the first thing times the derivative of the second thing, so plus e to the minus at times x dot of t. And if you look at that and you compare it to what's on the left-hand side of that equation, you say, oh, they're exactly the same thing. So indeed, all 3 of these terms on the second equation are identical to each other. Okay, so that's step 2. And then step 3 is as follows. We take the integral of both sides of part 2 and we set them equal to each other. So I've taken this middle term here and rewritten it here, and I'm integrating that term for dummy variable of integration tau going from 0 to t. And I've also taken the far right term and put that there, and I integrate that also from tau equals 0 to t. Now, on the far left side, we've got the integral of a derivative, and we notice, oh, this d tau here cancels with that d tau, and so I really have the integral of d something. When I integrate d something, I get that something evaluated between the limits of the integral. So I have this, the something is e to the negative a tau x of tau, so I have that evaluated between tau equals t minus the value at tau equals 0. So that gives me those terms right there. And we look at that, and we take these two things, put them together, and rearrange just a little bit by multiplying both sides of the equation by e to the plus at. If I multiply both sides by e to the plus at, then that term cancels out. Then I've got an e to the at multiplying this, which I bring over to the right-hand side, and it becomes this. And when I multiply this by e to the plus at, I can bring that inside of the integral and combine, and that's where I get this e to the at minus tau right there. So indeed, the solution to x dot equals ax plus bu is x of t is e to the at times x of 0 plus this integral from 0 to t that's shown there as the convolution integral. So what is our next step? Our next step is we want to convert a differential equation into a difference equation. And what we're going to do is we are going to evaluate the differential equation, that integral form, at discrete points in time in order to do so. So I introduce a connection between a continuous time notation and a discrete time notation on this slide here, where in discrete time I use brackets. So x of square brackets of k. And what that means, what that relates to in the continuous time domain, is x of parentheses or round brackets k times delta t. So it's not simply sometimes I choose square brackets and sometimes I choose parentheses. No, they actually do mean different things in this notation, where when I use parentheses or the round brackets, that's referring to a continuous time point in real time. And when I use square brackets, I'm talking about a sample number. So k is 0 or 1 or 2 or 3, whereas t could be any real value whatsoever. And this is the connection. So x at sample number k is equal to the input signal, continuous time signal x, sampled at real time k times the sample period delta t. Remember that we want to convert the x dot type of equation into an x square bracket k plus 1 kind of equation. So let's look at what x square brackets k plus 1 is equal to. Converting to the round bracket form, we recognize, oh, I have to substitute x square brackets k plus 1 equals x round brackets k plus 1 times delta t, which I've done. And then what I do is I take the equation from the previous slide, which was our result for x of t, and I put in t is equal to k plus 1 times delta t, and we get this result right there. What we do next is we take this e to the ak plus 1 delta t and we factor that into two different components. So it's e to the a delta t and e to the ak delta t. Not much change happened there. And then we take this integral and we also break it into two parts. And so if you think about some function that I might be integrating over time, and I want to integrate it between some initial time and some final time, call it tf, I can do that by integrating first up to some intermediate time, ti. I integrate under from 0 to ti, and then I integrate from ti to tf, and I add those two different integrals together. I get the same result as if I had just done one integral from 0 to tf. So we're taking advantage of that property. It's going to be helpful to break this integral up. The first integral goes from 0 to k times delta t, and the second integral goes from k delta t to k plus 1 delta t. And nothing inside of the integrand has changed at all. I've just broken up the limits of the integral so far. And then, when we look at that, we evaluate that a little bit more. Notice that this term here, I have factored that exponential of a sum into the product of exponentials, and that's going to help us evaluate that first part. In particular, notice that this e to the a delta t is not a function of the dummy variable of integration tau, and so that's a constant in terms of the integral, and I can bring it out. And when I do that, this is going to have a term in front that is the same, and I can combine those two things together in a convenient way. So that's what I do, noticing that this is part of that, and this is part of that, and what I'm left with, this term here, plus what's left over in that integral there, is what we would have called x of k delta t in our continuous time solution, or just x of square brackets k in a discrete time solution. So maybe it wasn't obvious why we were doing these steps, but I hope you can now see, oh, this result here is beginning to look like it could be helpful, because we've taken the x dot equals ax plus bu, and we've done some manipulation to it, and we have achieved, notice, xk plus 1 equals something times x of k plus a remaining term. So it's almost in the xk plus 1 equals something times xk plus something times u form that we want. In fact, this first term, e to the a delta t, is what is our discrete time a, the ad that we were looking for. And now we need to do some manipulations on this remaining term to make further progress. So to summarize where we're at so far, we have found that the new value of x is equal to a delta t times old value of x plus an integral. And we desire to simplify this integral, and in order to do this, we are going to start by assuming that the value of a is non-zero. It's a special case when a is 0, and we'll also look at that. And when we consider a being non-zero, we can break up this integral in a convenient way. We're going to assume also that the input signal u is constant over the sampling interval. So it changes from sampling interval to sampling interval, but over any particular sampling interval, u is constant, and it's equal to this form right here, u of k delta t. And so when we do that, within this region of tau going from k delta t to k plus 1 delta t, u is going to be a constant. So I can pull u outside of the integral. It's u of k. In fact, b is also a parameter value of our equation. It's constant, so I pull that outside on this side right here. And we're saying that a is non-zero, and I can factor this exponential term here, so I can pull outside of that integral this term, which is also not a function of tau. And so we have xk plus 1 is e to the a delta t times xk plus some exponential term times an integral times b times u of k. And this integral term is something that is not a function of the input, and in fact I can pre-compute its value. So we do that. We compute this integral. The integral of e to the negative a tau d tau is equal to minus 1 over a times e to the minus a tau evaluated between the endpoints, which is what we have here. And we can substitute what those endpoints are into the equation, and we get this right here. And we can further condense things by multiplying this through across that summation and distributing it across the summation. So what we end up with is when a is not 0, this is our discrete time equation. I have nu x equals this here, which we'll call ad, times old x plus this constant value right here, which we'll call BD. Actually, we'll combine it with B to call it BD, multiplying the input. So I have new x equals something times old x plus something times the input signal, which is what we had desired to accomplish. And now you see how we can compute AD from knowledge of A, and how we can compute BD from knowledge of A and B. So here's summarizing that. This is just what we saw in the previous slide. And for example, we can use this to convert the ordinary differential equation describing the resistor-capacitor circuit into one that is an ordinary difference equation, or a discrete time version. And to slightly simplify the notation, I've said that tau is equal to R times C, where tau is a time constant of the circuit. So the equation that we had before, we said that the time derivative of the resistor current was equal to minus 1 over tau times the resistor current plus 1 over tau times the input. And when we compare this to the generic form that we're trying to convert, we say, oh, well, the x on the left-hand side, I'm taking a time derivative of x, so x must be the resistor current in this case. And that matches because I've got on the right-hand side a constant times x, or a constant times resistor current, plus a constant times something else, so this must be u. That must be u in our generic form. So yep, u of k is equal to I of k in this equation. And then we say, oh, in the generic form, I have an a times x, so that value must be what we call a. And so a is negative 1 over tau 1. And then I have a b times u, so that value must be what we're thinking of as b, the 1 over tau 1. So we substitute these values into our generic result right here in this equation, and we say, okay, in discrete time, the next resistor current is e to the minus a delta t, or minus delta t over tau 1 times IR1. And then putting in 1 over a, that's going to be 1 over negative 1 over tau 1, or just negative tau 1. And e to the a delta tau is this, delta t rather, is this. And then the b is this minus 1, the plus 1 over tau 1. So we've plugged everything in. And we can simplify this a little bit by noticing this, I've got a tau 1 and I've got a divided by tau 1, and so those cancel. And the minus 1 I can distribute across these terms here to just switch their order. So I've got 1 minus e to the negative delta t over tau 1. And so that is our model for the resistor currents, how we convert that from a continuous time to a discrete time. I also said that if I was converting a generic equation where a was 0, that would be a special case. So let's look at that. Here's the same result that we had before, so nothing's changed yet. But now we will assume a equals 0, and we will assume again that the input is constant over the sampling interval. It might change between samples, but for any particular sampling interval it's constant and equal to u of k delta t. So when we do that, we go back to the previous slide and we substitute in this result. So we're starting here. We haven't performed the integral yet. So e to the a delta t, if a is 0, is just 1. So that's new x equals 1 times old x, which is what we have there, right there. And then inside the integral, notice if a is 0, all of that stuff is 1. So I have the integral of 1 d tau over the sampling interval, and then the bu of tau factors out as bu of k because u is constant over that time region. And if I integrate 1 over 1 sample period, I just get delta tau. So I get this. So if I have a continuous time equation for which a equals 0, the discrete time equation ends up looking like this particular form right there. So we can use this in the state of charge equation, because if you look at that, you say, oh, the state of charge equation looks just like our generic equation. If I say that the generic value of x is z, so I have x dot or z dot on this side, Normally I would have a times x on the right-hand side, but in the state of charge equation, there's no a times z. In fact, it's 0 times z. So that's why this special case applies. And then I also have, in the state of charge equation, minus eta divided by q times I. You say, oh, well, negative eta over q must be the b parameter. So I have a equals 0, b equals negative eta over q, x is replaced by z, and u is replaced by I. And when we substitute all of those values into this equation, I have new state of charge equals 1 times old state of charge, and then minus eta times delta t over q, all times the input current. And that's exactly what I claimed was the discrete time solution a couple of lessons ago, but now you can see how to derive that a little bit more formally. So our present model is now converted from continuous time into discrete time. Whereas before I had the state of charge equation dz by dt equals negative eta over q times I, and I had the derivative of resistor currents with respect to time was equal to negative 1 over R1C1 times the resistor currents, and then plus 1 over RC1 times the input current, and I had voltage equals open circuit voltage minus R1 times IR1 and minus R0 times I. All of those can be converted as we've seen. So in the previous slide, you saw how we converted the state of charge equation. The slide before that, you saw how we converted the resistor currents equation. And then all of those combined together into the voltage equation that you see right there. So the conversion is done. And everything that you've seen so far has been converted from continuous time to discrete time form. I recommend that you keep this slide handy. It's going to be convenient to refer back to it in the future to see all of the equations of our discrete time cell model in one particular place. So, to summarize what you've learned in this lesson, we've just remembered that it's often easier to derive models for circuits in continuous time first, but our final application is going to use these models in discrete time. So we needed a method or a process to convert a continuous time model into a discrete time model. And we have done that now for a linear first order ordinary differential equation. We found generically, except when the constant a equals 0, we could convert this time derivative of x dot equals ax plus bu into a difference equation where next x equals e to the at times present x, plus 1 over a times e to the minus at minus 1 times b times the present input u. In the special case where a equals 0, we had a slightly different result where x dot equals ax plus bu converts to next x equals present x plus b times delta t, all times this input signal u. And we applied this process to convert all of our continuous time cell model equations to discrete time. And in the next lesson, we're going to look at a practical and very simple way then to use an actual laboratory test on a physical cell to find the values of the cell model. We're going to find R1 and C1 and R0, for example. So we're making really excellent progress. We're only halfway through week 1, and the cell model that you've learned about to date is very commonly used as is. There are some refinements we can make, though, and so the remainder of the week we'll talk about even more of these refinements to make our final cell model that we'll be using in the remainder of this course and the remainder of the specialization.